In this project, we're modeling the amount of chlorine gas or chloramine gas in the air of a large indoor water park. This is a result of evaporation that occurs on these surfaces. These are water surfaces. We're looking at a CAD model where you can see water surfaces. And what we're trying to do with the computational fluid dynamics is to predict the amount of chloramine gas that comes off the surfaces of the water. Chloramine gas is the result of chlorine mixing with nitrogen. The nitrogen is coming from people. So as people get into this water, with the sweat from their body and other fluids get into the water and create chloramine gas. Chloramine gas is heavier than air and it floats on the surface down low. It wants to sit down low. If it gets into the breathing zone of humans in this water park, in this indoor water park, they're going to both smell it and feel it. In other words, it's something called swimmer's lung. When it gets into your lungs, it causes irritation. So the designers of this particular facility contracted us to perform analysis to determine whether or not there was going to be sufficient airflow, flushing of clean air into the environment to dilute the chloramine gas to a safe level. Now the WHO has a range for this. They're looking for this range to be in between 0.3 and 0.5 micrograms per cubic meter of chloramine concentration in these areas. So we built models for this and we're able to predict it. The way you do that is to take the CAD model to begin with, which was provided to us by our partner in this project, and to look at all of the diffusers and model all of the diffusers. As you can see in this image on the left, we're modeling air coming out of each of the diffusers in the environment. So we set the flows to be exactly what was specified in the architectural drawings and put them in the room. And then we can look at the amount of air that is passing over the walking zones. You can see a walking zone here, walking zone around here, and determine concentrations of the mixing, the chloramine gas in the air. So these are various images showing the air coming down out of the diffusers and into the room. Entrance of the park, other places. You can literally walk around inside here and see the concentration. This is a walk area here. You can see the air coming out, bouncing off the walls and coming down and flushing. Quite a bit of air over the water areas, of course, because they're trying to make sure there's enough clean air into the environment to dilute that gas. And you see a few shots here of us modeling that and showing where the air is coming in. We're coloring it here by velocity, because that does make a difference. You want the air to be slow enough so it doesn't feel like there's wind blowing on you, but yet fast enough and volume high enough so that you get the proper refresh. Generally you want air to be in the, if you're looking at feet per minute, you want it to be in the 100, 150 range when it gets near people. That way it doesn't feel like there's a whole lot of air on your body, because that will cause a cooling effect on you. So here is the various sections. This is another water slide here that's, or some kind of water, lazy river, I guess. Here's the lazy river over here. This is a wave generator, so you can surf on that. All kinds of fun things in here. And there's also fabric diffusers that we modeled here. They use some fabric in this environment. Here's the lazy river going down and the air coming into it. So there's a few of these shots. Then there's the returns. You also have to get the air back to the cooling system, so you can see it going back into the returns up in this region. Now then what we did is we started to look at the concentration of gas as a cloud, and you can see it building up here. So you can see the concentrations. Now remember, 0.3 is bad, so we're well below that range, and we've colored it so you can see it. It turns out they had plenty of air in this environment and they weren't going to run into any issues with chloramine gas. But we wrote a function called a user-defined function in Fluent that predicted the amount of chloramine gas coming out of here based on literature we found, and then we're able to visualize it so you can actually literally see it. So these are shots of chloramine gas, and you can see it building up on these water surfaces. Not in the range of anything to be worried about, but still you can see it. You can set that range so that you can see where it's building up and watch it be flushed. And so we worked together with the design build architects on this particular project to predict that, to adjust their diffusers a little bit so that it pushed it out or diluted it out of these regions quite nice. The kids' pool area had a little bit more than some of the others. And you can see from a top view, this is a slice. We're looking down at the environment at a particular height, and you can see the concentrations in some area are higher. And so you adjust your positioning of your diffusers and of your HVAC system to try to minimize that. Very good application of CFD for an indoor water park. In this case, they were fine. They were well below the 0.3 mark, so we were able to confirm that their design was quite good. We also made recommendations about the fabric diffusers not being ideal due to the low exit velocities. And there are some areas where concentrations were higher, but it could be improved, and the design team went ahead and did that. So that's a good example of using CFD in an indoor water park application to look at the effects of chloramine gas in the atmosphere. It can be applied to any kind of gas. It doesn't have to be chloramine. You can do the same thing for any other type of agent that you want to model in an air environment. Thank you.